telling us about the NASA's latest and greatest new space telescope, the James Webb Space Telescope, and in particular doing transient science and all of the work he did to get James Webb up and running and get us these cool images. So Armin Rest from Space Telescope, please take it away.
No. Oh. Can you?
Yes.
How do I go?
Nope.
How do I go forward and backward here? Okay. All right. So. Doesn't A. Doesn't work.
Yeah, okay, so there you go. So just use left and right.
It's on.
Co-host has asked you to start video.
It starts slideshow.
No? Give us a second here, please.
It's early in the morning, you know.
Yeah.
Yeah.
Yeah, this time it's not audio, it's just keynote. A PowerPoint. So you press the slideshow button. Yep.
Okay. Okie dokie. Good morning, everyone. Thanks for coming at 8:40 in the morning. I know that's a true sacrifice.
Hey, Alan, hide the floating meeting controls.
The what?
That bar on the top.
You do what you want.
Alex, could you please not do that?
Okay, here we are. So, again, good morning, everyone. Thanks for coming. My talk today is about JWST. I think you probably heard about it. JWST is, has really been coming for a long time, like a really long time. But I think all of it was worth it. It really is a new era, and I don't say this lightly. It is a new era in depth, resolution, and also in wavelength range. When you look at these images and compare to some of the images that we have, that we had before from HST, ground-based, Spitzer, from all of these telescopes, it really is an amazing difference. And this picture here, where you see a Webb image and a Hubble image, doesn't even do it justice. I will show you later on. When you zoom in, you actually really see the difference in resolution, depth, and wavelength range. So when JWST was planned, there were 4 major research areas that it was targeted for. I think one of the most important ones was to look for the first light. We wanted to look back in time as far as possible, and of course you have to go into the infrared because of the redshift to do that. And that's the main reason that JWST is in the near infrared and mid infrared. Other really important topics are galaxy assembly and formation of stars and planets. And I think also one of the most important things is to be able to look at planets and the atmosphere and to look for the origin of life. There was this one press release image, not image, the spectra of the atmosphere of the planet, and I have to say, this was the one thing that blew me away most. I still remember when I was like a little kid, we had never detected really a planet before. And then we started with having a handful of planets. By 5 years ago, we had 5,000 planets with Kepler and now TESS, and now we are there and we're looking at atmospheres of exoplanets. I mean, this is just like absolutely amazing. So how did this all start? In '96, that's, as I said, it has been coming for a long time. At Goddard, they were like doing the first drawing literally on napkins and kind of like thinking about what do we need to actually achieve that, to look back so far in time. And it's not an easy thing because, of course, in the near infrared, you have to cool it down, you have to protect it from the sun, and it also has to be big that you have the aperture to actually do this. And so in these early stages, this is kind of like what it looked like. And so they had the first studies, and this was a design with the sun shield and the telescope. It still looks a little bit strange. And then, of course, it's developed over the years, and now this is basically what we have now in space. It really is an amazing piece of technology with this sun shield here, and then you have, of course, these segmented mirrors, 18 segments. Putting all of this together is truly an amazing thing. So how did we get there? Very, very slowly. I think I don't have to tell anyone what a painful journey this was. So I started at SDSCI in 2010. At that point, we were supposed to launch in 2016. And yeah, that didn't happen. And so, I think you probably have seen this plot where you show when the launch date was predicted versus the actual time. And luckily, it wasn't the slope of 1, even though for the last few years, it always seemed to be 1 year away. I mean, literally, But we actually did converge, and this year we finally launched and got this piece of this observatory in space. And so we launched, and I think to really appreciate what actually was done, let me show. So let me show this video. So there are 200 moving parts in this telescope. And all of this unfolding is done after launch in this about 1 to 2 months that it takes to go 1 million miles from Earth to L2. And think about, you have like this sun shield and you are unfolding it and then moving it apart to have the full efficiency. And all of that has to work. I think, I don't know what the official, point of failures were that, it just like it would have not worked, but there were at least 10 complete points of failures. If anything would have gone wrong there, it would have been, pretty much a disaster. And a lot of people were sweating bullets, when we get the telemetry and like we hear stuff and things like that, and you're always like wondering when the time comes where there's like, oh yeah, we actually have a problem. Like one of the sun shields didn't fully deploy, or like, just like the unfolding of the secondary mirrors, unfolding of all of the segments, anything goes wrong and you're done. And when you think about how much work it takes to just commission a telescope on the ground with 5 people all around and hammering and moving and putting all things together, to do this on this scale, on this size, in space, so many kilometers or miles away from Earth, is just like a real amazing feat. So yes, it took a long time, but I think it was absolutely worth it. So I still remember this night, So everything was going well. We were at L2, and it was like, okay, tonight we're turning this thing on. We're taking the first images, And just, I was like at home. Unfortunately, I didn't have shift in the mock because that would have been absolutely the killer. I'm also not the A team, At that night, we had the absolute A team in the mock, in the mission operation control room at SDSCI. And, so I was sitting at home, on the voice loop. You hear it all, you chat with your colleagues. And then the first dark frame comes down, and you open it up, and it looks like a bias frame, just like what you had before. And I've never been so happy to see a bias frame, a dark frame before in my whole life. And then we were waiting, and it was like, okay, so first images are coming down now. We waited until they are available, and you download it and you pop it up. And so what you see here is we were taking a picture of a cluster, and the cluster was located here. All of these stripes are basically stars. And they're coming from all of these different segments. So the segments are not aligned. They're like, pointing everywhere. And that means you have like 18 different images potentially of each star. And when you look at this image, you see like some extra cluster here and some extra cluster here. So these were like two segments that were actually reflecting the light of the cluster from this point, and we're showing it here. So now you have this telescope that has these 18 segments that are pointing all over the place, and you have to align it to this really, really high accuracy. And so how do you do this? So the plan was, or what we did was, we take NearCam and we do this really big mosaic, 0.5 square degrees. 1,500 NearCam images were taken. And so the goal is, there's this one bright star here. We try to find all of the images of all of the 18 segments. And the expectation was that these segments will be distributed all over the place. And this was our room at SDSCI with all of the people that were responsible for the alignment. Marshall Parent was leading that. And it got really crowded during that time because, this was this was one of the most important moments. Can we now identify all of these images so that we can actually align these things? And actually what happened, let me just go back here. We were so lucky, or things worked so well, that literally all of the images were like right here. It was like amazing. And I just want to show this little video. Oh, there's no sound. Oh.
That is beautiful. Oh my God.
And so that's when they actually went to these images, and suddenly everywhere were all of these images from the 18 different segments. I mean, it was like amazing. They couldn't believe it. They just couldn't believe that it all worked out so well. And you can see there.
Wow.
And yeah, it was just it was amazing, man.
All right, we're gonna go home now.
So, okay. So now you have these 18 points that are completely jumbled up, and you have to align them. And this is the last video that I will show. So this was our original alignment here. They were all over the place. And so the first thing that you have to do is you do the first guidement, and you try to align the segments in the same way that you have the mirror up here. And then you align the secondary mirror. That is like done here. And you start to focus. That's like the first attempt. And then you stack all of these images. That's the first attempt to stack all of the images in one point. And you all move these up here. You always see which mirrors are moved. Then here you go to the coarse phasing with a Hartmann sensor, where you look at the phasing and you adjust it. And then you put it at multiple points of the field of view, and try to make sure that it all works in the different part of the image. And you can see slowly it starts to look better and better, and things are improving. But these are days and days and days of work that they have done. And you apply this corrections. This is still the coarse multi-field. And you move it back in the right shape. And after you have done that, you move one of the segments out that you can guide. You move it again around. You set up the image array. And very soon you do the fine phasing. Again, the image array. Here you defocus, and you go through different focus positions to try to figure out the best focus and also adjust the segments again a little bit. Here you adjust the segment positions. Now you gather again all of the segments, you put it all together, and you do the first fine phasing here with different defocusing. That was already a pretty good picture. I mean, everybody, at that point, everybody was like, yeah, pretty much, even if we have no improvement here, we are already in really, really good shape. And you go through another coarse phasing here, where you measure the segment pistons, now in this case. And the second fine phasing with defocusing. So here you can already see, again, better than the last fine phasing. And it's repeated one more time, round 4. One more coarse phasing, this is the last one, to measure the pistons again. Fine phasing 3. And I think now you're complete. And that is the final PSF of James Webb. I mean, it was just like absolutely amazing. And it exceeded expectations, I mean, you have like this range, it's like, okay, this is what you really want to be above. This is like when things go really, really well. And it was just like another step, another magnitude above it. It was really amazing how well everything worked. So, not everything worked perfectly, of course. There's still some warts and some issues. And so, as expected, we did get hit by what's called the micrometeorite. It's just like what you have at that position. And that was all fine, that's expected. And so you will have a slow degradation of the mirror and of the instruments because of that. But then we did get hit by one micrometeorite, this one here. And that one was with a significantly higher energy than was expected. And, of course, some press was like blowing it up and saying like, oh, micrometeorite hits and NASA cannot correct it. And it sounds like as if like, it hits James Webb and we are just degraded and we will never have good images again. It's actually not true. So these images at the beginning, we will never have as good as images as these first images because you actually cannot correct for that. So we will have a slightly worse PSF than this first one, still much better than expected. And I think we lost about 1% throughput, something like that. So you don't want to have, 50 of these in the next 2 years. That, of course, would be bad. But the hope is that this was just like an outlier, like the kilonova in 2017, where we all thought we will get like kilonovas, another 5 in 03 and like 50 in 04. And I think right now we are glad if we find, at least 1 in 04. And so here we're kind of like hoping the same, that this was just a bad outlier that happened in the first 6 months, and we don't have these hits every 6 months, but maybe every 2 or 3 years or something like that. So, cross your fingers. It's not the end, and even if it would be every half a year, we still would have a very fine telescope for a long time. One good thing that also happened at launch, the launch was pretty much perfect. We saved a lot of fuel because we were already at the right orbit. And so the fuel is not really the limiting factor anymore. It probably should last for 20 years. The planned lifetime is 5 years. That's kind of like the minimum that we really want to have it. The expectation value was 10 years. And I think now how things are going, we could exceed the 10 years if you're lucky and nothing catastrophic happens at some point during the lifetime, which always can happen in, in space. So you probably have seen this. This was kind of like one of the first PR images that they put out, where they showed images of all instruments and how beautifully aligned the mirror was, or the telescope is. And the nice thing is we didn't really have to make any compromises that like, oh, we have to change it, that this instrument is okay and this instrument is okay. It pretty much like works equally well for all of the instruments. So just a couple of words to what is live in the MOC, in the Mission Operation Control Center at SDSEI. So we all had to do our shifts. You know, the NIRCam station is here, these two chairs. And I have to say in hindsight, this was really kind of like a life experience. You know, you always see it in the movie when they're sitting there and they all seem like as if they know the shit, you know. And then you're there yourself and you're like, oh my God, oh my God, oh my God. I mean, the first two shifts, I was like, you know, I was scared. I was really like, okay, don't screw up, you know, don't do anything wrong, don't completely embarrass yourself. Didn't always completely succeed, you know, but you learn and you get better, and after a while, you're okay. And we have a big team. It was a really good teamwork, and so we have our A team. Any issues, you're immediately on the voice loop, and you know, you see if any one of them is online to help out. It is kind of funny. I mean, you're like, you know, you have your headset on and you go through the stations, and when you are, you know, the lead of the shift, then it's like, okay, yeah, NIRCam is green and go, and then you do your thing. And once in a while, you have to change something in the timeline and do a change in the operation. And the one shift, I had to do that, and you know, you fill out all the stuff, and you have to mark the people that have to approve it. One of them is MOM, M-O-M, the Mission Operation Manager. He's truly the mom, you know, taking care of everything. The science instrument lead, and then a few other ones. And I, in my infinite wisdom, I also clicked on NIRCam, just like to be sure, you know. And so suddenly our voice loop becomes like, you know, NIRCam for mom on ops. I think you also have to approve your Oscar and Fisker. Was like, you know, everybody was chuckling. You know, we are all in this room. And so I asked that I have to approve my own little thing. And so, of course, I was not supposed to do that. And so I made a little bit of fool out of myself and, you know, got like red ears. But that's just like how it is. It was really fun. I mean, it really was a lifetime experience to be a small little wheel in that whole exercise and operation. So we got our big July 12th data release. You know, you couldn't miss it even if you want to. All of these beautiful images. We had some live streaming, and I heard that really went very well. It was definitely interesting. Well, it happens. It's not easy sometimes, and it was still an amazing event to see all of these images pop up. They really kept the secret. You know, I mean, I heard maybe a few days before a couple of rumors, what was observed and things like that, but they kept it secret even for the instrument teams. So, just very quickly, a short intro to the instrument. So NIRCam, that's the instrument I'm working on, and it is kind of like the workhorse for imaging for JWST. It goes from, you know, the optical from 0.6 microns all the way up to 5 microns. It has 2 channels, and the beautiful thing is it has a beam splitter, so you get one short wavelength and one long wavelength at the same time. Really nice, you know. The image quality is exquisite. We are pretty much like Nyquist limited now. It is really good. It's a 2.2 arc minute by 4.4 arc minute field of view. Excellent throughput, and that's like, you know, you have to look at this one here. 1.0 was what was in the ETC as throughput. And in the longer wavelengths from 2 to 5 microns, we have about a 20% more throughput than we had in the ETC. And the goal was to be above 70%. We were expecting to have water ice condensating on some of the optical elements. It didn't happen. We looked for it, and everybody was like, okay, we have to see a water feature here in the spectra, one of the first spectra. And they were not there. So we got really lucky. We were expecting that this might happen. There are some issues. There are wisps, claws, snowballs. There's like a stripe pattern, a bias. It's a 1/f noise that is difficult to get out. So there are some warts. We're still working on that. We're still trying to improve things. So here, just like very quickly, the wisps are here in the yellow. And these wisps, they're always there. It's just like scattered light that you get. And what we didn't expect was these claws. And that happened if a really bright star is at a certain position, pretty far away actually from the field of view. It just finds this hole to go through the optical system and scatter off to create these claws. And so we are working on trying to figure out what this region of avoidance is so that we can help the observers to not rotate a little bit in case one of these stars falls in this region. And this is a quick comparison that actually Justin did between HST, one of the first HST images, JWST images compared to HST. So this is HST, and you can see some of these galaxies here. And then when you look for JWST, I mean, you can see this galaxy here. It actually looks like a galaxy and not like this red blob here in the HST images. So when you actually zoom in, you can really see how much deeper and better these images are. When you just look at the press release images far away and you look at both HST and JWST, it's like, well, they look kind of like similar, different structure and stuff like that. But when you go into the details, you actually see that. MIRI is like the imager for the mid-infrared. It goes from 5 to 28 microns. It also has low-resolution slit spectroscopy from 5 to 12 microns. Sensitivity is excellent. PSF is excellent. And here you can see the real improvement because we never had in the mid-infrared anything that was comparable. HST doesn't go to this wavelength range. And so if you compare Spitzer to JWST, it's just like a difference of day and night. It's really beautiful. And NearSpec is the workhorse for spectroscopy. It has several modes. I think the most interesting one for transients it has a fixed slits. This one, a fixed slit with a low resolution. If you look for supernova, anything that has broad lines, you can go really deep, But it also has, higher resolution ones, 1,000 and 2,700, and you can do MOS and also an integral field spectrograph. So let's talk a little bit about transients because that's, of course, it's a topic here. Of course, when the images came down, we had our hack day at SDCI with, Justin, Sebastian, Mike Engesser, and grad students. Gina was there, and so we were going through these images, looking for a transient. Gabe Brammer, he's like a beast, He is super fast. He put out a tweet and was like, "Hey, this might be a supernova here." We pinged him and we worked together. And we got astrometry, as a photometry and astrometry, all correct. So this here is a JWST composite color image. You don't see much color here, but it actually looks really nice. This is the HST images. There's absolutely nothing here. You can already see it with your naked eye that there's some object here. Here is F1115. And if you do the difference images, you can see it's a really nice little transient here. So we got out this astronaut. and Mike Engesser led it, and also the other postdocs at SDSDI. It was really an absolutely fantastic time to just like do this, be together in the room with all of the other SDSDI people and try to make this happen. We also got images, and that was kind of like serendipitous with FANGS. I think it's an ERS program or a GDO program. And so FANGS observes these close-by galaxies, and we knew that in the galaxy that one of the galaxies it's observing, there was a supernova a long time ago, and actually it still is ongoing. There was supernova 2013 EJ, and ORI actually has a MIRI program to observe it in a few months. But they observed it, and they just missed it with MIRI. I have a video. I think the supernova is all the way down here, literally like 10 or 20 arc seconds of the MIRI image. That's a MIRI image, but it observed it in NIRCam, and we looked through, and this is like this supernova in this outskirt of this galaxy, and we put out an astronaut, and Justin and Sebastian and Mike, they are working on getting some photometry in all the different bands, and we will see what we can do with that. So the last thing, here is actually the light curve. Yes, so you can see the light curve here. So the last thing I want to talk about are high-redshift supernova with HST. Of course, that's like one of the most fun people to think about, to do, is to find these supernova of the first stars. And with JWST, and maybe in the future with Roman and with Euclid altogether, we might be able to do that. So we have put in a proposal in cycle 1, and we didn't get it through. I have to say, of course, it was also somewhat ambitious. We asked for 400 hours over 3 years, which is quite a chunk of JWST time. But in some way, I think it is really, it would be one of these legacy surveys for JWST, because you get both. You get the transients as well as very, very deep images. And the problem is when you apply through the tag, it's normally for 2 cycles. And you cannot do this with 2 cycles. The time scales for the transients is about 2 years. It's a cadence that you want to have. And so you really have to think about it on a 5 to 10 year time scale, and that of course brings it to kind of like, this is a legacy project, and the director has to approve that and put the resources in. So here's just like, here's a plot of simulated light curves, and you can see, of course, at that redshift from 6 to 12, you have these events are very, very long. First of all, they are longer than normal supernova anyway. Superluminous supernova are more timescales of hundreds of days. And then with a redshift, you really go to and they're going on for years. So that's actually a plus, because with a cadence of 2 years, we should be able to catch every supernova in the field. Maybe at later time, at late phases, but we should still be able to do this. So why are these important? I mean, these are the first events that distribute material into the surrounding medium, and then the next stars are formed with these enriched materials. So it is important to understand that for the formation of these next generation galaxies. It's important to understand their impact on the reionization of these massive, through these massive stars. And so I think it's a really great project. So here's the kind of like, when you look at F200W versus the color F200 to F444, what we can get to is about between 28 and 28.5 in a reasonable amount of observing time. And so this is like our limit here. The different colors are different types of supernova, from type 1As, type 2, and then here on the right side in red, you see superluminous supernova and pair instability supernova. This line here is kind of like our limit on F444. So what we are getting with a survey like that is this upper right part, and that's where these first supernova live in. The issue is we have foreground contamination. You imagine about 6 months before we have our epoch, we have a type 1A supernova go off. It peaks at 24th, it declines down to 26th or 27th. We don't know it's a type 1A supernova. We take an image, it's late, it might be reddened, it looks red, and we think it might be one of these early supernova, high-redshift supernova, and it's not. So we can guard against that by having ground-based surveys like Rubin, maybe later on Roman and Euclid, to monitor these areas. We don't even have to go super deep. Not as, of course, we cannot go as deep as JWST, but if we go to, let's say, 26 or 26.5 and do it regularly so that we get all of the supernova that are in the foreground, at peak, we know that later on when we take a JWST image, it is not a high redshift. And we can do awesome science because we get for free all of these near-infrared and mid-infrared observations of these foreground supernova as well. So I think this will be, if we can pull this off and do this, this will be an excellent survey and project. And we are very open to collaboration. We had already a pretty big team when we put in cycle 1. So if people are interested in this, just get in contact with me and, Ori and Lou, we kind of lead this together. And yeah, just get in contact. It would be really, really cool with Rubin. Now, basically, Rubin and Subaru are the only telescopes from the ground that have the field of view and the depth to do that. And I think actually Rubin is even better than Subaru because it is really hard to get enough time on Subaru to get the cadence to do this. So I hope that we can talk about which fields to actually observe. We are relatively flexible. We just have to take into account that we don't want to look at an area where we have too much extinction and too much stuff going on, so it has to be an extragalactic field away from the galactic plane, of course. But besides that, we are pretty flexible and open to to collaborate and to change our plans to make this happen. But I really think that, collaborating here, we really have to collaborate with these different projects, and then we will do that. So, just to conclude, I think we are in a new era. It really is an awesome instrument. I'm really happy how this all worked. The telescope does perform above expectations. We are, at the best of our expectations, or even slightly above for most of the things. There are still some warts and some issues, both with technical issues, with downloading data, with some of the calibration, some of the reductions. We worked really hard to try to make as much progress as we possibly could. Please be patient. Things will get better in the next half year and year. We did find the first transients, 2022 AUI and 13 EJ. And I hope that in the next couple of years, we will also start our high C transient survey. Thanks for your attention.
Thank you. Thank you so much. We have time for maybe one question. Yep.
Hey, Armin, exciting talk, and super excited about the high-redshift supernovae. But my question is about the micrometeorite impact. I get a lot of questions asked, how does it affect the JWST performance? I know there was a point where it says that there is ongoing efforts, but can you comment a little more about what would be the strategy to like, it's not the end of the world, I get it,
Yes.
but I just
So
wanted to.
what actually happens is that, you know, the mirror or the segment gets bent a little bit. And it's in a way that you cannot just adjust it by moving the pistons a little bit and changing it. So, so you wanted to know what effect it exactly has, or?
No, it's
It's-
like, what are the ongoing efforts to just avoid those contingencies?
It's difficult. So when there was this meteor shower, or where there was, you know, a higher density of meteors, you can put the telescope in certain positions where it's less likely that you're getting hit, you know. And so there might be times in the future where, when we know some stuff is going on in the area, that maybe your observations will be cancelled, and they will observe something in an area of the sky where the spacecraft is more protected. So, but besides that, you cannot do much. You know, I mean, you just don't know when one is hitting, and you just have to hope for the best. Yeah.
Thank you.
Okay. Thank you.
Thank you. We have questions in the Zoom chat. Maybe you can answer them. But it's a very short one from Ashley Villar saying, if I want to learn where is the place where I can find how to reduce James Webb data, where is it? Is that online or something like that?
Which data is online? I couldn't understand the question.
Like where to learn how to reduce
Yeah, so
JWST.
there are different ways. So downloading the data, I actually wrote a script that is public, with which you can download the data. Reducing the data, it's involved. There are a couple of really nice Jupyter notebooks that lead you through, for example, how to create mosaics. And they're all online at the STCI web pages and on GitHub. So there are tutorials, there are Jupyter notebooks, there are some tools. Orifox has some data analysis tools that you can use to look at the data and have a first look. So there's a lot of documentation online, and but you can also just like ping me, and I can point you to some of these resources. So it takes a little bit of time to actually download or like to install the JWST pipeline, and it is a big thing. It's not the nimblest pipeline, but you can actually use it yourself, and you can also change it. Justin, for example, has hacked some of the TweakReg code to be able to use your own color lock and your own XY positions to do the alignment.
Okay, great. Thanks.
Thank you.
Okay, thank you. Our next speaker is Danny.